the SS L'Hôpital. You are about to embark on a new mathematical journey with your two captains, the dorm room professors. Today, we will sail off into a new world, partial derivatives.
As we push off the docks, we will first explore what a partial derivative is. A partial derivative is used for functions with more than two dimensions. Its definition is each partial is the derivative with respect to one of the variables, while all the other variables are held constant. Note that this is not the same as the total derivative, where all the variables are actually allowed to change. For example, if we take the partial with respect to x, it can be notated in 4 different ways as shown on the screen. But the most common way is shown on the far right, delta f over delta x.
Alright, so now we're going to explain the geometric interpretation of partial derivatives. So each partial tells us the slope of the function with respect to one of the variables while we're holding the other variables constant. So for example, if your function of x and y is x squared plus xy plus y squared, you're going to get a shape that looks like the graph on the left-hand side of the screen. It's kind of hard to visualize a rate of change in 3 dimensions, so what we want to do is we want to put it in something that makes it easier to visualize, like 2 dimensions. And how we do this is we set one of the variables constant. For example, on the graph on the right, which is known as the y trace, we set y equal to 0. We would have gotten a very similar looking graph if we had set y equal to any other constant, but we chose 0 for simplicity. So when we set y equal to a constant, we're going to get a graph that in the shape of the parabola. And this tells us that if we take a slice of the function of x and y, we're going to get a parabola shape. So with respect to x, the function will change at a negative rate of change when x is -1, for example. It's going to have a slope of 0 when x is 0, and a positive slope when x is equal to 0.5 or 1. The 2-dimensional graph gives us the derivative of the function with respect to x. It's important to say that we can also do this while holding x constant and taking the derivative with respect to y, and in that case we would just be looking down what's called the x trace, holding x as a constant and taking the derivative of the function with respect to y.
Using the function of the previous slide, we can take both of the partials of this function. So we have f of xy equals x squared plus xy plus y squared. So if we take the partial f with respect to x, we do the power rule, which gives us 2x for the first term. The second term we leave y constant, so we just treat it as a constant, so the derivative of x is just 1, so it's 1 times y. And then there is no x term in this, so this is just a constant, which then becomes 0. So it equals 2x plus y. If we then take the partial with respect to y, we get, this term doesn't have a y variable in it, so that's just a constant. And then this term would then become x times 1. And then this term we use the power rule to give us 2y. So then we could put these together to give us the overall gradient of the function, which gives us the slope in the x direction while y is constant, and then the slope in the y direction while x is constant. So this looks like this. 2x plus y, comma, x plus 2y. All right, so now we have found both partials of this function.
Excuse me, professors? I was just wondering, since I know that we can take the second derivative of a normal function, can we do it with partials too?
I'm very glad you asked, because it's actually the same as with partials as it is with regular derivatives. So we could take f, the second derivative with respect to x, is just going to be the derivative of this term right here, which gives us 2 times 1. And then this term does not have a y in it, so it's just going to be 0. And then the double of y with respect to y gives us just 2. And then this is just 0 because it doesn't have y in it. Since this was the second derivative in the x direction, we could also take the second derivative of x in the y direction. So this would just look like this. This is the partial of x, and then if we take it again with respect to y this time, it just looks like that. So we're taking this, the derivative of this with respect to y, holding x constant. So this term is just going to be 0, and then the second term here is going to be 1. We could do the same on this side. So this is the partial with respect to y, and then we take it again with respect to x while holding y constant. And that's going to give us 1 plus 0, since this is a constant.
Okay, so now we're going to do an example in 4 dimensions, and also we're going to use higher powers. So we have our function, come on pen, of x, y, and z, and that equals x cubed plus xy plus yz plus x plus y squared, excuse me, plus z to the 4th. Okay, so the first thing we want to do is take our partial derivatives. So we're going to take the derivative of f with respect to x, the partial derivative of f with respect to x, and that's going to be all the terms with x. So we're first going to get 3x squared, and then we're going to hold y as a constant, so we're going to get plus y. And there are no other terms with x, and everything else is a constant, so that's all going to go to 0. And then we're going to take the partial derivative of f with respect to y. We're going to look at the terms of the y. So we have this term, the second term here. X is treated as a constant, so we're going to have x plus, and it's going to be the same thing here. Z is going to be treated as a constant, so we're going to have x plus z. And here we're going to use the power rule to get 2y. And there's no y term in the final, there's no y in the final term, so that's going to be the derivative with respect to y, and then the derivative of f with respect to z is going to be the same process. So we're going to get y plus 4z cubed. This is going to result in the gradient, where we combine all of the partials. So that's just going to be 3x squared plus y, comma x plus z plus 2y, y plus 4z to the 3rd. We're going to take the second partials, and notice that we have powers greater than 2. So now all of our constant terms, all of our partials will not be constant terms like they were in the last example. All right, so let's get started. We're going to have 9 partial derivatives because we're going to have 3 partial derivatives for each partial that we already took. Okay, so first we're going to have the second partial of xx, and that we're going to look at the first partial. We're going to take it with respect to x, so that's going to equal 6x, and y is a constant, so it's going to be, its derivative is going to be 0. Then we're going to have f of x, y. We're still going to look at the first one. We're going to take it with respect to y, and we're just going to get 1. And then we're going to look at the first partial again, f of x, and take it with respect to z. But since there are no z terms and everything else we're treating as a constant, it's going to be 0. So now we're going to move on. We're going to take the second derivative first with respect to y, and then with respect to y again. So now we're going to be looking at the middle term. And we're going to see that that is going to equal 2 plus the derivative of x, which is a constant, which is going to be 0, and z is also going to be 0, so we're going to get 2. And then we're going to have f of y x, and that's going to be with respect to x, so we have 2 constant terms, the 2y and z, which are both going to be 0. We're going to be left with the derivative of x, which is 1. And then we're going to have f of y z, and we only have 1 term with z, so we're also going to have 1. And now finally, for our last 3, we're going to take the derivative with respect to z, the second partial with respect to z. And we're going to get 12z squared with respect to z, and then we're going to take it with respect to x. And since there are no x terms, it's going to be 0. And then with respect to y, we're going to have 0, and then the derivative of y is going to be 1. And there are 9 second partials.
This production of Dorm Room Professors was brought to you by Le Pen, Brunette, Hazelnut Praline Spread, produced in the magnificent country of Belgium.
With the sound